Everyone, in this video we're going to go over base and arithmetics. So now let's talk first about positional notation. So that is a very important concept when we're talking about representing a number. So when we take a number, every digit value depends on the position, which is going to be in terms of the powers of the base. So pretty much if we have a base, let's say b, then we can represent the position of a number by the digit value multiplied by the power of the representing the position. So just to give an example of that in base 10, which will be familiar, we will have 347 in base 10 is just what? Well, we have 3 on the hundreds, so that's why we multiply 3 by 10 to the 2, which is 100. Then 4 is in the tens, so that's why we multiply 4 by 10 to the 1. And finally, we have 7, and 7 is the units, so we're going to go with 10 to the 0. So notice that this number has 3 digits, and hence we got to go with 10 to the 2, 10 to the 1, 10 to the 0. The same idea is going to work for any base. So the third position is always going to be power to the 3, the second position power to the 2, the first position power to the 1, and the initial position or digit position or the unit position is going to be the position 0. So in base 2, we will have something in the position 3. It will be like multiply by 2 to the 3. Then in base 8, it will be by 8 to the 3. And base 16 will be 16 to the 3. Okay, and so on and so forth in the different positions. You see 2 to the 2, 8 to the 2, 16 to the 2, and position number 2. And position number 1, we have 2 to the 1, 8 to the 1, and 16 to the 1. And similarly, in position 0, we have 2 to the 0, 8 to the 0, and 16 to the 0. Now, some of the tricky bases that you're going to be using when you're working on your IT majors are going to be the binary, the octal, and the hexadecimal bases. So the binary is, of course, using 1, and that is used by hardware, logic gates, memory. The octal goes from 0 to 7, and it's a compact binary notation that is used in some cases. Hexadecimal is used in memory for colors and machine code, and it goes from 0 to 9, and of course from the letters A to F. And there's a representation that goes for each of those. So for example, the hexadecimal letters A, B, C, D, E, F are seen in different ways. In decimal, this is representing A is represented by the 10, B is represented by the 11, C is represented by 12, D by 13, E by 14, F by 15. And binary, you have the conversions. For example, A is 1010, B is 1011, C is 1100, D is 1101, E is 1110, and F is going to be 1111. Now, the digits 0 to 9, of course, are going to mean the same in all three bases. A through F are only going to be part of the hexadecimal base. Now, let's talk about converting between bases. The method for converting base n to decimal will be using the positional weight and do the sum. So for example, if we're transforming a number in binary to decimal, then we're going to pick each of the numbers and we're going to check the positions that they are, and we're going to multiply by their base, and that's going to give us their value in decimal. So for example, here we have 1, 0, 1, 1 in binary. So because this is on the third position, then this is going to be 1 times 2 to the 3. Then 0 is in the position 2. So it's going to be 0 times 2 to the 2, 1 times 2 to the 1, plus 1, 2 to the 0. So that's going to give me 8 plus 0 plus 2 plus 1, which is going to give me 11. So this number, 10, 11, and base 2, is just going to be the representation for 11 decimal base. Now we can do the same thing with other bases, like for example, let's change octal to decimal. So we have 347 in base 8, and we want to transform that to decimal. So again, we do the same thing. In the second position, we have 3. So we do 3 times a power to the 2 plus 4, that is in the second position, times a power to the 1 plus 7 times a power to the 0. Okay? So now we can do the same kind of thing for hexadecimal to decimal. Now we're going to have here 2a3 and base 16. So we do the same thing as before. In position 2, we have 2 times 16 power to the 2 plus a and base in the hexadecimal base. Remember that will be representing 10. So this will be 10 times 16 to power 1, and then 3 times 16 power to the 0. So we're going to have 512 plus 160 plus 3. That's going to give me 675. So now that was for converting base n to decimal. But now let's do backwards. Let's do, if we have a number in decimal, how do we transform that number to base n? And so what we had to do is we gotta repeat the division. So we're pretty much gonna divide repeatedly the target number by the base b, and the remainders bottom to the top are gonna work out as or significant digits for the number. So let's give an example here. Let's transform 25 base 10 to binary. So first, I divide 25 by 2. That's going to give me 12, and it's going to give me a remainder of 1. Then we're going to go with, okay, so now we have 12. We're going to divide that by 2. We get 6. So we get a remainder 0. Then we take 6. We divide by 2. We get a remainder 0 as well. Quotient 3. And then now finally we get this 3 divided by 2. It's just going to be 1, and the remainder is 1. And then finally we divide 1 by 2. The quotient is going to be 0. There's no way that I can fit 2 and 1. So that's going to be quotient 0, remainder 1. So now notice the way that this goes. The first number to start is going to be the first remainder that we have left. So notice 1, 1, 0, 0, 1. We're going in this direction. So 25 in decimal is 1101 base 2. Now let's do the same thing with an hexadecimal number. So let's transition 675 base 10 to hexadecimal. Here we're going to have 675 divided by 16. That's going to give me 42, and the remainder is going to be 3. Then we're going to take 42 divided by 16. We get that as twice, and we're going to have a remainder of 10, or 8. And then finally 2 divided by 16. We don't have 16 is going to fit here, so it's going to be 0 times remainder 2. And so now, once again, we can represent 675 in base 10 as 2a3 in base 16. Notice that we'll start from here and we go to here. All right, so let's talk about some fast conversion between binary, octal, and hexadecimal. One octal digit is 3 binary digit. One hexadecimal digit is usually 4 binary digit. So if we want to convert, let's say, this 10, 11, 0, 1, 10 base 2, what we do is, if we want to convert to hexadecimal, we group them into nibbles of 4 bits from the right. So for example, we can see this as 1, 0, 0, 1, 1, and then 0, 1, 1, 0. Notice that we're just break it into groups of 4. And so notice that from before we saw that this was 11, and then this is going to be 6. So we're pretty much going to have that this is just B6 in base 16. We're breaking it in pieces of 4 bits. To octal, what we do is we break it into triplets. and we go from the right. And well, of course, we're gonna pad the left with 0. So for example, if we have 0, 1, 2, this is just 2. Then 1, 1, 0, this is gonna be 6. And then 1, 1, 0, this is once again 6. So we can see this as 266 base 8. Notice that you can find this number very easily because you are doing the expansion. Remember, this is position 3, so this is 0 times 2 to the 2. This is 1 times 2 to the 1, and then 0 times 2 to the 0. So that's why it's going to give me 2. In this case here, we have 1 times 2 to the 2, and 1 times 2 to the 1. So you have 4 plus 2, 6. So that's why we get 6 here. Okay. So here's the check-in for doing that. 11 times 16 plus 6 is going to give me 182. So this is one way to check that this is doing this correctly. And 266 on base 8 is also 182 on decimal base. So that way we know that this is working correctly. We just compare with the decimal base since this number in decimal base is this. All right, so now let's talk about arithmetics on base n. So the rules for adding to binary digits is, of course, we're gonna get carry when we get pretty much at the end of a sum 1 by 1. So the way that this goes is like let's check binary digits here. So if we have like let's say a b coming in, saying the sum coming in here is going to be 0, and what we have coming out is going to be 0 as well. If we have that you have a carry is 1, then the sum is going to be out 1, and the carry out is going to be 0. This is pretty much how much am I carrying out. If I have a 0 added to 1, then the carry in is just going to be 0, and I'm not adding anything. The sum is 1, and then the carry out is going to be 0. This from this table is kind of hard to see, so to continue doing this instead, I'm just going to check what is the sum of 1, 0, 1, 1 in base 2 plus 0, 1, 1 in base 2 as well. We're kind of adding in decimals. This is 11 plus 6, which should give you a 17. So that's something that we're going to verify later. So notice that we're adding this number with this number. So 1 plus 0 is just going to be 1. And we don't have anything else. We don't need to do anything else. 1 plus 1, then because it's base 2, 1 plus 1 will be 2. But 2 on base 2 is really the 0. So we got to the 0. We're carrying 1 here. Then similar than here, we get 1, 0, and then we go 1, but we were carrying 1. Now here we get the sum of 1 with 1. Once again, is going to be 0, and we carry 1. And then we get 1 plus 1 plus 0 is going to be 0, and we're going to carry 1. So we're going to get this number here. Okay? So now this 1, 0, 0, 0, 1, if we put this in terms of finding out how much this is in decimal base, we're going to find that this is 17. This is 1 times 2 to the 4, which is 16. And then 1 times 2 to the 0, which is 1, then 17. Very quickly, you can realize that that is the sum. So now let's do binary arithmetics. So the rules here is like a decimal subtraction, but it's with base 2 borrowing. So borrowing 1 from the next position is going to give me 2 instead of 10, like in decimal base. So let's look at an example here. We're going to subtract 10, 11 base 2 minus 0, 1, 10 base 2, which is essentially subtracting 11 minus 6, which will be give me 5 and base 10. Now notice we have here 1 minus 0. That's going to be 1. I'm not borrowing anything here. I don't need to. 1 minus 0 is just 1. Now I have 1 minus 1. 1 minus 1 is just going to be 0. I don't need to borrow anything, so 0 here. Now I have 0 minus 1. So obviously I can't do that because I have 0, so I need to borrow from before. But if I'm borrowing, the rule tells me that this is like having a 2. So if I'm borrowing 1 from the next cipher, then I'm going to have here 2 minus 1, and then that's going to give me 1. So 2 minus 1 is 1. And now I go to the next one, but the next one I borrow for this one. So this is going to be a 0 because I borrow 1. So 0 minus 0 is just going to be 0. So here that means that 1, 0, 1, 1, 2 minus 0, 1, 1, 0 base 2 is going to give me 0, 1, 0, 1, 2, which is essentially 1 in position number 2. And 1 in position 0. So this is like 1 times 2 to the 2. So this is 4. And here is going to be 1 times 1. So 4 plus 1, 5. So I can prove that this is 5 on decimal base. So we're good. Now there's an alternative method in which subtraction a minus b can be done as a sum, like 2 complements of b. This is also how modern CPU will implement the subtraction, not separate subtract circuit needed in here. But that's something that you can check computationally and kind of research how it's done. Now for the multiplication, it's a different entire matter. The rules are even simpler. If you have 0 multiplied by anything, it's just going to be 0. And if you have 1 multiplied by anything, it's just going to be that anything. Partial products are just going to shift of the multiplicand, and then you're going to add. So for example, if we have 1, 0, 1, 1 multiplied by 0, 1, 1 base 2, we're doing here like 11 times 3, 33. That's going to be my end result in decimal base. Notice what happens here. If I have 1, 0, 0, 1 multiplied by 0, 1, 1, initially we'll start with this 1. So this is going to replicate this number. 1 by 10, 11 is going to give me 10, 11. Now here I'm going to move to the next position, and I'm going to have 1 by 10, 11. So 10, 11 here, a copy. And then the next one, I'm going to move 1 position more, 0 by this. I'm going to have the zeros here. So at this point, the only thing that I have to do is add. Now when I'm going to do the sums, then the 1 goes down. 1 plus 1 is 0. And then I'm carrying 1. Then 1 plus 1 is 0. And I'm carrying 1. Once again, 1 plus 1 is 0. And I carry 1. 1 plus 1 is 0, and I carry 1. 1 plus 0, 1. So you get this as a final result. And when you figure out what this is in base 10, then you're going to have that this is 33 base 10. All right, in the next video, we're going to see sign and binary representation and other parts of n-base arithmetics.